To.
Okay, I'm going to just introduce Federico. Federico is an associate professor at the University of Milano Bicocca, where he teaches human-computer interaction, interaction design, and information systems. Thanks very much, Federico. Over to you now.
Yes, good afternoon, and thank you for the nice introduction and for inviting me in such an interesting event. I am an associate professor of human-computer interaction, but I also work as a senior researcher into teaching hospitals of Milan in northern Italy. And I don't know if I can change my, yes. There I deal with artificial intelligence, supporting the work of physicians and nurses. But I don't do it from the point of view of the typical artificial intelligence expert, the one who develops machine learning models and then deploys them in a given clinical setting. Rather, I do it from the point of view of the expert in human-machine interaction. I'm an interactionist. I like to design and study collaborative protocols between humans and machines to see how these two worlds can coexist and possibly help us to improve medical practice. When I present myself as an interactionist, and I have to explain what I have to do with AI applied to medicine, I usually sketch a diagram like this one. You see, it's like a closed loop where clinical practice informs the development of AI systems, and these in turn affect clinical decision-making. Now I show this sketch to you closer. Obviously, the relationship between human beings and
maar daar in dat grijze doosje, deurtje voor een cadeautje of zo.
It was intended to me?
No, sorry, can we ask everybody please to mute themselves?
Okay. I was saying that this relationship is so complex, in particular, whenever we want to put these machines in a certain work context, into the real world, into the mangle of everyday practice, so to say. So our common aim is to bring value to the experts who work there, because this is the best way to bring value to patients and improve outcomes in a sustainable way. Of course, as scholars in this challenging field, we can focus on specific stages of this circular flow of information between intelligent machines and human experts: advice provision, decision-making, the coding of new medical facts, the training of predictive models with this medical information. But no matter what ambit we decide to focus on, there is an important fact to recognize. This flow is far from being continuous and seamless. In fact, we better see there are at least two large chasms which prevent the world of machines where I work and do research from informing and shaping the world of care where doctors work and where we stay as patients if we suffer from any health problem. For the sake of argumentation, let's give these two chasms a name. I'll call the first gap separating machines from doctors the chasm of human trust, and the second one, the gap between medical practice and model development, the chasm of machine experience. These are just names. I'm not good at names, but it's just to pinpoint two elements that, in my opinion, are crucial in this relationship between us and the machines. Okay, looking at any chasm requires us to think about possible bridges if we don't want to end up in one, right? To this aim, in my opinion, we have to focus on processes. Processes that are mostly carried out by humans and that are definitely centered on humans. The processes by which we can promote trust in the machine's advice, so they regard validation and explanation and dare to say persuasion and many other things like user experience, user interaction design, and so on and so forth. And the processes by which we produce, process, engineer medical data. So where we have to care about data quality, like reliability, the presence of biases, representativeness, etc. Because, if garbage in, then garbage out. It's well known. Since I only have a few minutes today to bore you with both of these aspects, we are in any case very interconnected and mutually influential. In the next few minutes, I will focus on the aspects on which I have focused my recent studies, how we build trust around medical AI. Well, do not forget, I'm just an engineer. So when I have to think about a concept, I often make do with the dictionary definition or the common sense meaning. So trust, what's trust? We trust someone or something, as in the case of a decision support system, an AI, if we believe it is reliable. And this simply means that we find it trustworthy. Trust is a complex concept that in the specialist literature is often associated with qualities like reputation, capability, predictability, integrity, and benevolence. If we have to speak about the integrity and benevolence of an AI system, we could think this acts for the good, is there to help us. But we should still reflect on these concepts, building up our idea of trust, because we should not forget behind an AI system, there is always a programmer, the employers, and who pays their salaries. In short, there are the AI vendors. Are these always benevolent? This is a good question I leave open for now. But I cannot dismiss the other qualities so easily. Reputation in terms of perceived ability and predictability, because these are core for the common concept of accuracy of the decision support system, and to a smaller extent of the idea that the accurate performance we are told a system exhibited at validation time will be repeated other times, will be reproduced at our hospital or setting, okay? And we are continuously told by experts and researchers that medical AI systems are very accurate. And they report on sound meta-analysis and reviews published in high-impact articles, like this one published on Lancet Digital Health, one of the first ones to claim that AI systems perform on par with the best ophthalmologists, dermatologists, radiologists, and sometimes they are even better than them. So through the mass media, the social media, and the specialistic literature, we are overwhelmed with this idea that AI systems are more sensitive and than specific diagnosticians that are, fallible, far from untiring, and most of it human. Well, I remember a music video where a gorgeous Shania Twain was wearing a leopard skin suit that to my 20-something-year-old eyes must have looked as daring, as incredibly sexy at the time. And she sang, well, this doesn't impress me at all. You remember that song? And it's true, we should not be impressed if someone tells us that his system is almost 100% accurate. And you know why? For at least two reasons. First, as we know, even DeepMind, a society controlled by Google, is having a very hard time trying to achieve the performance of the successful predictive model for the detection of diabetic retinopathy, a model that was presented in a famous study published on JAMA in 2016, and since then cited more than 3,000 times. That model was trained on high quality and carefully vetted pictures taken in few top-notch hospitals in the US East Coast and boasted a receiver operating curve of a whopping 99%. The same model exhibited quite a poor accuracy on dirty, dark, poor pictures taken at the Indian facilities where this model was deployed to contrast this invalidating and widespread disease. The problem lies in the fact that the Indian data were deeply different from the American pictures in terms of quality, of course, but possibly also in terms of technical specifications and production modalities. As we shown in an article that we have just submitted, there is a strong positive correlation between the similarity of validation datasets with the model training set and the accuracy scores obtained on the validation tests, validation datasets. In this article, we make the point that these similarities should always be assessed and verified, and possibly the validation dataset should be chosen as different as possible, to be as different as possible, so as to get a conservative and more reliable estimate of the actual performance of the predictive model on real-world data. Whatever, nobody does it. Second, let me state this clearly. The current way to assess the accuracy of predictive models in medicine, as in other fields, is pure fiction. It is common knowledge, a discursive practice in which the premises are clearly false, that the random variables are all independent and identically distributed, that the parameters that optimize the model are optimal, that all the data on which the model will have to express itself will come from the same distribution. And I could go on and on. But everyone is fine with this fiction. We reported this in a technical article written with the collaboration of 12 radiologists, which we entitled "The Elephant in the Machine." That is the subject that no one wants to talk about, but everyone is very aware of. There we propose a new metric to assess the reliability of the data that are used to train a predictive model. And we also provide a practical nomogram to adjust the actual accuracy of a machine learning model as a function of the reliability of its data. In this paper, we also made the point that if you can estimate the diagnostic accuracy of the raters you involved in the ground truthing process, you can determine how many raters you should involve to get a dataset that is at least 95% accurate. For instance, if you get very good radiologists in your team who are even more accurate than average radiologists, you need 7 of them. It goes without saying that most of the machine learning models are trained with gold standards that are labeled by just 1 or at most 3 independent raters. Radiologists are expensive resources, as you know. On the other hand, if the accuracy narrative is flawed, what can we do other than complain, point out to everyone that the king is naked, and just look like grumpy fanatics who are a bit eccentric in the medical machine learning community? Well, we propose a new metric that grounds on the concept of accuracy, but tries to go beyond it and point to a different level, that is the level of the utility of the diagnostic or predictive model for the clinical practice. This is the formula of the new metric, which merges the best approaches today to define accuracy and the net benefit. That is a famous metric to estimate the utility of a classification model. That's why we called our metric weighted utility. I obviously don't mean to be rude and bore you to death with the technical details of this metric, but I still want to talk to you about the idea behind it, because for me, it is the approach that deserves some attention. With such a proposal, we want to say that intuitively, a decision support is useful if the number of times it is right in detecting a health problem is higher than the number of times it is wrong. So, easy, right? But our observations in the field of work and long conversations with the domain experts have made us sensitive to the fact that this is not enough. A useful model is also a model that, first, is optimized to avoid the most impactful kind of error, that is, false positives or false negatives, because not all mistakes are equal in medicine. Second, the model helps doctors when they need it most, that is, for those specific cases that are most difficult to interpret, or for those that they see less frequently, for instance, because they don't work in a tertiary specialized hospital, or those cases that require faster feedback because they conceal a condition that needs to be handled as quickly as possible, and therefore also an automatic preselection, so to speak, would be good. You could ask how this can be accomplished, practically speaking. My obvious, almost candid answer is let's involve the clinicians, who are the real experts of what is useful for their daily work. Then you have to imagine that this metric is fed on the basis of a process in which the machine itself asks questions of a group of experts or even the individual user in order to better assess its performance in terms of utility. For example, by asking, what's the impact of a false positive on an ordinal scale, or any other sensible way to assess the impact of overdiagnosis, of overtreatment, overuse, also including patient anxiety or discomfort. Assuming these can be quantified, obviously, even in a subjective and arbitrary manner, this is the coefficient tau in our formula. If you think that the subjectivity inherent in our endeavor to define tau is unbearable, know that you can also extract a sensible answer from the diagnostic behavior of doctors themselves, looking at whether they naturally tend to avoid false positives or false negatives. For instance, as you can see, for knee MRI images, the radiologists we involved tended to avoid false positives, which imply new tests and maybe unnecessary surgery. In the case of oncology, it would probably be the opposite. Doctors would tend to avoid false negatives. Then we can ask doctors how relevant they find each individual case on which we want to assess the quality of our diagnostic model. This assessment helps us to formulate the R coefficient in our formula. And even here, the concept of relevance of a case is obviously a conceptual quagmire. We have, of course, assimilated it to complexity, but obviously it can be a combination of several independent and complementary factors. And there are different approaches to assess quantitatively how important it is not to misdiagnose a certain case. One objective way is to see how many doctors have misdiagnosed the case. In this case, relevance is assimilated to the concept of decision complexity. Or one can survey doctors in terms of expectation. A case is more complex the higher the specialization and experience needed to diagnose it correctly. How surprising it will be for a novice, for example, to identify it correctly. And the last point, now I want to ask you, would you like the doctor who is treating you to flip a coin to see what disease you have? Probably not. Well, this is exactly what models, what predictive models do when they determine which category to associate with a case, and their probability score or confidence score is low. To determine whether a person has skin cancer, even the most accurate of models published in JAMA can do so on the basis of a probability of 51%, and often does so for probabilities lower than 75%. So our idea is to find out what minimum confidence a model must have for a doctor to find it useful to give advice. Perhaps because they think that an advice given by flipping a coin is unhelpful and probably misleading or conditioning. This is embedded in the sigma part of our equation. In our research, we have always published the results of our models when they are at least 75% confident of their output. Obviously, this reduces the so-called coverage. This is the number of cases for which the model can provide an advice, but this is not important for us as we take automation bias seriously. This threshold can be set also in empirical ways. For instance, by considering the average confidence expressed by the ground truth raters when they are to label the training cases. You see here, each joy plot is a single radiologist telling us for each MRI how confident they were for each diagnostic label they had given. These obviously depend on how difficult the cases were and also how expert they were, the doctors were, or better yet, felt to be. To conclude, as we asked in the title of one of our recent pieces, who wants accurate models? Actually, we want useful models. And gathering reliable information about the potential usefulness of a model is crucial because this information underpins the reputation of the model itself and thus the trust that clinicians can place in it when they rely on it. So I have two take-home messages to share. First, as designers of predictive models or as prospective users, please evaluate the similarity between the training dataset and the validation set by means the accuracy of a model has been evaluated. As prospective users or people involved in the procurement of such a model, please demand that this to be done. demand better evidence of effectiveness and accuracy and reproducibility. Second, developers of machine learning models should always weigh their data for what clinicians really care about. This could be relevance, complexity, rarity, whatever. The important point is to consider that every piece of data which describes and represents a clinical case hides an entire world that we must somehow bring to light in order to make our utility estimates as reliable and responsible as possible. So I believe that changing our perspective on how we should evaluate a model is a question of responsibility, because it also essentially regards the deep reasons why we should trust such a tool, and therefore accept our decisions are affected by such a tool, for better or for worse. But that's all I have to say for today. I can't add any more. Thank you for your attention.
Thank you. Thank you very much, Federico. There's lots to discuss there and lots to connect with our with what we were saying earlier about validation as well. If we can go on now to our last paper, the last presentation, which is if Federico, you can stop sharing so that Karen is going to share her slides now. So our last presentation for today